Okay. All right. So I'm happy to welcome Matt Fredrikson back to Wisconsin. He was a student here back, I think he graduated in 2015. We overlapped briefly. And he is now a professor at CMU. And he's been, he's, I guess, crisscrosses many areas, but he's officially a security slash, with some formal methods background, but he's been doing a lot of great work in machine learning, exposing bugs and bias. So join me in welcoming him. Go ahead, man.
Thanks, House, and it's great to be back. Thanks everyone for showing up. Right before the holiday week. I wasn't sure, what people's plans would be, but since we're probably all stuck, fairly close to home, I suppose might as well spend it hearing each other talk about research. Okay, so today I'm going to talk about some problems related to privacy and fairness in applications that make use of machine learning, and discuss some techniques that we can use to sort of surface the causes of some of these bugs and gain insights into potential solutions. So just some kind of background motivation. Of course, machine learning is everywhere these days. It's being applied to sort of help make decisions in a pretty wide range of applications, things from credit rating and employment screening, healthcare. It's even being used in various aspects of law enforcement, from predictive policing that looks to do things like allocate police resources based on historical data, even to decisions about pretrial release. So one sort of contentious application of machine learning in recent years has been recidivism prediction. So when a defendant has a sort of bail hearing, oftentimes now aspects of their criminal record and other things, demographics and so forth, are fed to a machine learning algorithm, which makes some assessment of how likely they are to skip bail if they are released. Right? So of course, when something as sort of impressive sounding and fancy as machine learning is applied to all of these various problems that operate on individuals' personal information, this gives rise to concerns. In particular, concerns about privacy. So how are these applications actually using people's personal information? Are they using it in a way that might expose it unnecessarily, or in a way that would sort of run contrary to norms? And also with regards to fairness, right? So in that last example they talked about with recidivism prediction, one of the reasons that this has become so contentious is findings that the algorithms that people had been using to do this seem to be biased in some subtle ways. So just a concrete example that I think sort of speaks to the privacy concerns around machine learning applications. This came from an article that I read in the New York Times, probably back in 2013 or 2014, and it was about a marketing campaign that Target was doing, and it was it doesn't seem like that long ago, but when it came to sort of applying machine learning to these sorts of applications, it was still sort of early days, and they were talking about one sort of module in their system that was trying to predict whether their customers were likely to be pregnant or not based on their shopping history. And this article sort of was interviewing some of the data scientists who worked on that, and they were talking about being able to do things like identify like 25 products that, when you analyze them together in the right way, give you a pretty good pregnancy prediction score. So things like a shopper who buys cocoa butter lotion, a large purse, and some dietary supplements that pregnant women commonly take, their model assessed was fairly likely to indeed be pregnant. So the privacy issue here, I think, is predicting somebody's sort of sensitive health information without any explicit input that would seem to indicate that, right? So sort of a bunch of kind of weak signals that, when combined, let you infer something pretty personal and potentially sensitive about someone. And the article even had some anecdote where there was like a teenage girl in Minnesota who started receiving flyers from Target in the mail with her name on them. And they seemed targeted, and they were advertising sort of pregnancy-related items, right? Like baby shower gifts and diapers and formula. She was still living with her parents. Her father gets the mail. He saw this, contacted Target, was quite upset that they were suggesting something about, or seemed to be suggesting something about his daughter. But of course, in this case, it turned out that his daughter was indeed pregnant. And I think that sort of illustrates like sort of the core of this sort of privacy issue, right? Rather than his daughter sort of being able to choose when she informed her family about her situation, it sort of happened involuntarily for her based on her shopping history. Okay. So that example, I think is actually a little bit different than a lot of the privacy and fairness issues that are arising in machine learning applications today. Primarily in that, like, Target intentionally tried to do this, right? Their goal was to use machine learning to predict sensitive information about people from a whole bunch of other correlates. An issue with a lot of models that people are using right now sort of comes from accidental or incidental misuse of personal information, right? And it sort of follows from the fact that a lot of machine learning models are essentially black boxes, right? Take a really large and complex deep neural network, feed it terabytes of training data, and it makes really good predictions, but we really don't have any idea, or it's difficult to get a clear idea of how the model is operating, right? So we can think of this as applying to something like a hiring model, where an organization gives a whole bunch of applicant data to the model. It returns decisions, and they come back biased. And the question is, of course, like, why is our hiring model favoring men over women, or vice versa, right? And this isn't hypothetical. This happened a couple of years ago. Some of you might recall this news about Amazon scrapping an AI-based recruiting tool because their internal tests showed that it was biased against women, right? And given the sort of gender disparity in large tech companies, not just in the United States, but across the world today, this was seen as a sort of non-starter, right? And what sticks out to me about this is that a company like Amazon, right, certainly has a lot of talent that if there was a way to sort of salvage this, right, if they had made this investment and thought that it was going to be worthwhile, and they hit this issue and saw their best option as just abandoning the tool altogether, I think that probably indicates that this opacity issue is very real, right? And is a serious roadblock when it comes to understanding and addressing these issues when they arise. Okay? So in the first part of the talk today, I'm going to sort of describe, how we can characterize privacy and fairness issues in machine learning models as stemming from harmful use of protected information. Right. So when it comes to problems of fairness or discrimination, this might mean, for example, using race or gender to make employment decisions. Right. Of course, it's rarely as black and white as, you can never use race to make any employment decision ever, right? There can be business necessity exceptions. And I think one of the attractive features of this view of fairness as harmful use of protected information is that the techniques that we have to sort of unearth it might give us a means to identify like when the use of race for an employment decision sort of meets the criteria of being a business necessity exception. Right? Similarly, when it comes to privacy, we might think of using like health or political background for marketing, right? And in fact, several countries have regulations that are considered to be privacy regulations, which say exactly that protected health information can't be used for certain purposes, right? And similarly, and as with reasoning about exceptions when it comes to fairness, there can be comparable exceptions with privacy, but in framing the sort of harmful behavior in these terms, we sort of put things on the right footing to be able to think about those exceptions as they come up in specific applications. Right, and sort of a theme that I think underlies like both of these issues, and being able to identify uses of this protected information is that like the opacity of machine learning models really enhances the threat, right? So when developers are trying to train and incorporate machine learning models into their applications, they don't know how information is actually being used, so they don't necessarily know if there is going to be a fairness, discrimination, or privacy issue, possibly until it's too late. And on the other side, auditors who are tasked with checking these applications for compliance with regulations have a more difficult job when the models that are being used are opaque and difficult to sort of verify these claims against. So sort of outline, for the first part of the talk, I'll dive into this framing of privacy and fairness as information use. See how we can sort of actually formalize this and get a meaningful definition of what a sort of protected use information violation looks like, and also some tools to help us uncover them. And then in the second part of the talk, I'll discuss some more recent work that leverages some of the tools and techniques that we've developed to help us understand information use towards understanding a particular sort of privacy vulnerability in some machine learning models where sort of very specific features from the training data end up getting memorized and can be recovered by an attacker. Before I continue, are there any questions? Okay, feel free to interrupt me if there are. Okay.
So Matt,
yeah.
This is Samesh. One question I had is, so on this feature memorization issue, have you seen this recent work by Vitaly Feldman, which says that models with very high capacity,
yep,
in order to get good accuracy, have to memorize part of the data? Have you seen it? It's actually just a very recent work.
Yeah, absolutely. Yep.
So in some sense, what I'm thinking is that if you want your models to be accurate, maybe you had to give up some privacy.
Yep.
You have
Yeah.
anything to say about that, or?
Yeah. Yeah. Absolutely. And I can return to that when we get to that part of the talk. I think
Okay.
that's a really interesting paper. We've read it like 4 times in my group meetings over the past year, I would say.
Okay.
And okay, so like one thing to take note of with what he showed in that, with what Vitaly showed in that paper, is he does talk a bit about privacy and sort of the implications for doing accurate private learning, maybe being, you know, at odds due to his findings. What he doesn't show is that when this memorization happens, it can actually be exploited, right? And so like I think that's a bit of a key difference between the way I'll characterize it later and what he did. But yeah, that's an excellent question, and that was a really nice paper. Yeah.
Thanks.
Yep. Okay, so to understand information use in machine learning models, we'll start out with sort of the base case, so to speak, where the model explicitly takes a variable that encodes a particular type of information as input, right? So think about a really simple credit model, right? It's going to decide whether somebody should be passed on for further consideration for a loan, or denied outright, some kind of a low pass filter. And sort of syntactically or structurally, this model takes 2 inputs, age and income, but semantically it only makes use of one of those features, namely income, right? Now, if we have, you know, a hypothetical individual who submits his age and his income to this model and sees that he's denied, right? His application is not going to be further considered. Right? You might ask, okay, was I denied because I don't make enough money, or I make too much money, or something to do with my age, right? Am I being discriminated against because of my age? So one observation is that because sort of in real data, age and income are somewhat correlated, it might be difficult to sort of ascribe blame or conclude that the model is in fact discriminating on the basis of age, if all that we can do is feed the model samples from the sort of real distribution of features corresponding to individuals, right? Instead, what we can do is try and sort of probe the model to understand whether age is causally influential on the final decision, right? So the idea is that we basically want to break the correlation between age and income, right? We can do that by fixing a value for income and then sampling values from age from the target distribution, right? And in this case, we would see that the model's decision doesn't change because the income stayed the same, right? And of course, when we do the same thing with the income variable, the model's prediction is going to change, right? Fixing age and varying income. And from that, we could conclude sort of just by probing it in this black box manner that income must be influential and age isn't, right? Another way to think about this is sort of in terms of information flow. Like whenever I say influence for the remainder of this talk, we are talking about this notion of causal influence, which if we're looking at you know, model as a program, means that there's like flow or interference from some input or some state of the model to its output. Right. Okay, so that's sort of the basic case where the.
So
yep.
Matt, this is Sumesh. Are you when you say causal intervention, do you mean it in sense of causal learning, or do you mean something else?
No, yes, that's an excellent question. I do not mean it in the sense of causal learning. Sort of, I guess, like practically speaking. So like, what do I do here? Causal learning.
Because there is a very special semantics to this term intervention.
Yeah. So okay. So with causal learning, the idea is you're assuming that the data comes from from some distribution that you have, like, you know, some kind of operational graph that can describe it, right? Some structure that sort of dictates how the random samples from the distribution are generated, right? And you can intervene on parts of that structure to sort of measure the effect of the corresponding variable on the rest of the features, right? So here, like, we're not assuming any causal structure in the data itself. What we're after is the sort of causal influence within the model, right? So how much influence does like an input, like the age input to the model, have on the decision, right? So that's why I was sort of drawing this comparison to information flow. You might also think of this as like a kind of quantitative information flow, right?
Okay.
Yep. Okay, so that was the easy case. But in practice, it's often true that the information type, or the sort of protected attribute that we're interested in measuring this influence on, isn't explicitly given to the model, right? So this would have been the case in that target model from earlier, where pregnancy wasn't an input to this sort of ad marketing model. Instead, all of these correlates of pregnancy were, and they had some classifier that essentially inferred the pregnancy variable, and then used that to compute the ad display, right? So what we want is a way to determine that something like a random variable is inferred by the model and then influential on its output. Okay. So how do we do this? Well, first of all, like we need a working sort of consistent definition of what this sort of inferred or proxy information use means. So let's like try and axiomatize it, right? The sort of first axiom that might come to mind would be explicit use. Namely, if some random variable is an influential input of the model, so it's an explicit input of the model, and the model actually uses it influentially to compute its result, then that model has proxy use of that variable z, right? So the second case, preprocessing, sort of corresponds to the previous slide. Basically, if model A makes proxy use of some variable, right, and A prime, right, is equivalent to A, except it takes an additional input, or sort of A prime is equivalent to A, except on replacing the explicit variable with some function of its input, then A prime must also make proxy use of Z. Right. So really, what we're trying to capture here is that A prime simply infers some piece of information that was explicitly given to A, right? If these two functions are completely equivalent, then we want to be able to say that both have proxy use of our protected variable. Right, axiom 3. So basically, if a model like sort of takes some variable and doesn't do anything with it, and it's equivalent to a model that sort of doesn't operate on that variable at all, then it also has proxy use. So basically, non-influential variables shouldn't be able to change whether a function has proxy use. Right, and finally, something to sort of rule out some instances. If all of the inputs to a model are independent of the protected variable z, right, then we don't want that model. We don't want to say that model has proxy use, right? So if a model isn't given any information about the protected type, there's no way to make proxy use of it. So these 4 axioms seem reasonable. They seem reasonable to us. They sort of capture an extensional like black box view of what proxy use might be. By the way, are there chats that I should be monitoring? Okay, no, you guys.
I can, if someone writes something in the chat, I can ask. Yeah.
Cool. Yep. All right. But the problem here is that these axioms are actually inconsistent, right? So there is no definition that satisfies all 4 of these axioms simultaneously, right? And the sort of like intuitive reason is that this preprocessing axiom, right, uses functional composition, right, and asks and sort of insists that we preserve proxy use under uses of functional composition, right? And we needed that to be able to talk about inference, sort of the core of the definition, right? But the rest of the model can essentially like cancel out a composed proxy, right? And conflict with the independence axiom number 4, right? So a concrete example of this, if we have X, Y, and Z, say they're pairwise independent binary random variables, and Y is equal to X exclusive or Z with probability 1, right? Then a model that takes Y exclusive or Z makes proxy use of Z. That's by explicit use, right? And so does the dummy model, where we add X as an input but don't actually do anything with it yet, right? Note that Y is not defined as X exclusive or Z, so it's not like we're syntactically subbing in X exclusive or Z in A prime here, right? It's just that Y is statistically equivalent to X or Z, right? And finally, by preprocessing, if we replace Y with X or Z, right, that's going to be equivalent to the original, but here we violated independence by replacing Y with this function, right? We're left with just X, and this violates our assumption that all of the variables are pairwise independent, right? So these extensional axioms don't serve us well. They don't sort of give us a path to being able to define proxy use. So how do we fix it? Well, the approach that we took was, instead of relying on functional composition, we replaced that with the notion of syntactic composition. Right? Basically, the way that we handle preprocessing and inference is directly tied to how the function is represented as a program. Right? So one sort of upside to this that we'll see is that we can actually use this definition to check for proxy use and identify witness computations in the model. So we can actually point to a location in the program that comprises a predictive model and say, like, this is the culprit. This is what is making proxy use of gender or race or whatever. This also gives us a consistent set of axioms. I won't go into them in detail. They're very similar to what I showed you, but they replace anything having to do with composition with this syntactic form of it that we'll discuss in a minute here. But the one sort of main downside, at least that I see to this, is that now that, like, the only way that we have of expressing composition is tied to the representation, like, as a program, we really do need white box access to whatever model we're checking or auditing, right? Okay, so let's talk about this sort of syntactic mode of composition a little bit more. And we'll actually frame it in terms of decomposition. So basically, given a program P, what we want to be able to do is express it as a triple consisting of 2 programs, P1 and P2, and some fresh variable, so that basically, if we replace X with P1 inside of P2, we get the original program. Okay? So to make this concrete, say that our program is a simple decision tree like this. We would basically think of P2 as sort of the outer program, right? And P1 as some like subprogram or subterm or sub computation, right? And we would obtain P2 by replacing that subterm with this fresh variable x. And then we want to talk about influential decompositions, and that merely means that inside of P2, we can change the final value of P2 by changing x. So basically, x interferes with the final value of P2, and we refer to that as an influential decomposition of the original program P. Okay. So now that we sort of see how we're talking about composition, the only other prerequisite to get out of the way is what we mean by proxy, and by this we say a random variable is a proxy for some other one if there exists some functions that can make them statistically identical, right? So Z is a proxy for X if we can find F and G such that processing X with F gives us Z, and processing Z with G gives us X. Okay? This might seem a little convoluted, but basically what we're capturing here is some notion of two-sided statistical association. If we want to quantify proxiness, right, you could think of proxy as corresponding to something like a lot of mutual information between two random variables. So then our program has proxy use of some random variable Z if there exists an influential decomposition of it, and the subcomputation P1 is a proxy for Z, or it's associated with Z. So just one quick note, we can also phrase this definition inductively over the structure of the programs that we're reasoning about. The sort of base case that you want to think about there is explicit use. Pretty literally that explicit use axiom, or the existence of some computation that's a proxy, and then the inductive case would follow from the syntactic composition with something that we already know as a proxy, right? So the advantage of framing this inductively is that, like, if we do have if the structure of our program sort of admits a well-founded induction, then we actually have a method for checking proxy use purely syntactically, right? Assuming that we can accurately measure the association of each decomposition of the program with a given random variable.
Matt, this is Tom.
Yeah.
Can you go back to the previous slide?
Mm-hmm.
I'm a little confused about one thing, which is that I would have thought highly correlated would have been a relevant notion here, whereas you're saying that you've got these functions where the probabilities are 1.
Yes. Yep, you're absolutely right. Okay, so I would call this perfect proxy, and I didn't qualify it just to sort of like keep the nomenclature simple on the slides, but that was exactly the point that I was about to get to on the next slide, is that if we actually want to use this in practice, right, like this definition, especially the notion of proxy, is almost always too strong, right? We probably want to be able to quantify the degree of association between subcomputation and a random variable, and maybe sort of like set tunable thresholds for what we're willing to consider strong enough.
I see.
Yeah.
Okay, I have another question, which is that when you that came to my to mind when you move from this semantic notion to syntactic, or this
Yeah.
axiomatic notion to syntactic. So are you saying, I don't think you're saying that there is no semantic criterion that one could use. In fact, from your analogy with information flow, I thought that you were probably going to do something where you could vary one variable and see how much effect it had on, or one collection of variables and see how much effect it had on another collection of variables.
Yeah.
And then maybe do self-composition or something like that. So
Yeah.
as an operational method.
Yes. Okay. So, like, first of all, I do mean that like there is no semantic notion that satisfies these axioms, right? So like these axioms are inconsistent. If this is what you mean by proxy use, then there is no like, and I would say that these characterize a semantic notion of proxy use. Like the fact that they're inconsistent tells me that there is no workable definition to be had, right? But I get what you're saying about like, so non-interference is a definition. Like why can't we build a notion of proxy use out of non-interference, basically, right? Is that sort of where you're?
Yeah, something like that. And well, in fact, it almost seems like you started in what I would have thought was the right way, looking at the semantics, and then backpedaled to syntax, which is kind of the contrary to what happened in the information flow community, where a lot of the early things were kind of based on syntactic stuff, and the operational or even ad hoc things about how to pass things, about how to look for things in the control flow graph or the abstract syntax tree, but before things got straightened out with the right semantic definitions.
Absolutely. And sort of chronologically, that is how we approach this. Like we tried to arrive at a semantic definition first, right? And we couldn't, like literally for 3 months. So I think over the summer of like 2016, like we just like kept shooting down definitions on the whiteboard, finding sort of inconsistencies and counterexamples. When we decided to like actually try and axiomatize it, and found that like the only axioms that we could agree on were inconsistent, we felt like, okay, we'll settle for something syntactic. But okay, so like to say a bit more, I think the issue. So there are two issues. The first is that we are like trying to characterize some notion of like information flow with like internal to a program. So instead of talking about just information flow from the inputs to the outputs, right, which things like which definitions like non-interference are perfectly capable of doing, we're sort of asking about a definition that says, does there exist, an information flow from some intermediate state, which is, by the way, correlated with a random variable that affects the output, right? So I think that's one sort of like that's one issue that is like leading to this inconsistency, right? And the second is like the addition of insisting on like independence, meaning proxy freedom, right? Like if what the program is computing can be expressed as a function that's independent of a function over a variable that's independent with z, right? Then we don't want to call that proxy use. And that's exactly like what led to the conflict in our counterexample here, right? So yeah.
So Matt, I have piggybacking on Tom's question.
Yep.
So there is a lot of literature on axiomatizing sort of causality, like with Jody, which your remark, by the way, you should revisit that because a lot of those, your axioms reminded me of axioms in Judea Pearl's book.
Well, I read Judea Pearl's book the summer that we did this work.
Okay, yeah, but the thing what I find it very weird is those axioms are trying to characterize the data distribution, have nothing to do with the model, right? Mm-hmm. They're basically saying how your probability factors. To me, that makes more intellectual sense because I could have a crappy model, right? Suppose I say, oh, if there is a full moon and the person is male, then I will give them a job. If it is a dark night and it's a female, I'll give them a job. So so the idea is I find it kind of intellectually, there's a dissonance in my mind that your axioms are trying to characterize the model rather than the underlying data distribution.
That's because you're, okay, I see where you're coming from, but I think where you're coming from is kind of a machine learning perspective, right? Like you're thinking in terms of like given some characteristics about the data, what's the right model to use? Like how do we get that model, right? And there, I think understanding the causal structure of the data would be very useful, right? Because you ultimately want to build a model that does the right thing in light of that causal structure, right? But the whole goal here is to say, like, we don't care how the model is produced, scikit-learn, trained a model, TensorFlow, trained a model, whatever. It's been given to us. Like, our job is to figure out whether it is inappropriately using some protected variable, right? So we're sort of like, I'm coming at this like a software engineer or a bug finder. And the only thing that's relevant to me, like the data is certainly relevant because like we're primarily interested in how the model behaves when it's applied to data that comes from the right distribution, right? But if we're looking for bugs in the model, right, then the causal structure of the model to me is what's like, that's the only way that we're going to be able to find bugs in the model is by considering that.
Okay.
Does that make sense?
Yep, that makes sense.
Yeah. Okay. All right.
You're basically saying I should not hang around with the ML people like Kamalika too much and do more work with Tom.
Yeah, you've been hanging out with the ML people too much. I think so.
Okay,
yep.
Good.
Yep. Okay, so that is our definition. I don't think that there is a single author on the paper who wouldn't express some disappointment that what we have is essentially a syntactic definition. It was a bit of a letdown, but nonetheless, it has proved useful. So one of the things that we can do is with things like functional classifiers that can be sort of expressed over some grammar of operations and conditionals, things like random forest, decision trees, rule lists. We can think of a decomposition, again, purely syntactically as a subtree of the model's AST, and its enclosing context. And then the notion of influence that we use there is basically the probability that the sort of intervened model produces a different classification than the original model on pairs of inputs, x and x prime, sampled from the targeted distribution, right? And so we have applied this to reasonably large models trained on, at this point, mainly proxy data. And by proxy data, I mean publicly available data that sort of looks and smells a little bit like the sorts of sensitive information that credit models or predictive recidivism models might be trained on, but they're public and so like not quite the real deal. We've also applied this to regression models. In the case of linear regression models, one nice thing that we have is that because the models only ever sort of do addition and scalar multiplication over random variables, we can actually sort of think abstractly of random variables in this setting as vectors in some vector space where covariance is their inner product, right? And so what this leads us to, right, is that influence is like a function of the norm of a vector. I think it's actually like the squared Euclidean norm, and association, right? So linear association is just covariance. Given two random variables as vectors, their association is going to be a function of the angle between them. And so sort of graphically, if we're interested in thinking about, in reasoning about proxies for some random variable z depicted as a vector here, right, then the sort of space of proxies that we want to worry about are going to be, let's see if I can do the laser pointer here. I don't know why it's not working. Sorry about that. Basically, any vector that extends into, like, past the yellow circle. So this yellow circle would correspond to an influence threshold, right? A space of vectors whose Euclidean norm is greater than some quantity. And the pink shaded regions would correspond to all of the vectors whose angle is less than some association threshold, right? So what that suggests is, if we have a model, you know, alpha 1 with coefficients alpha 1 and alpha 2, right? This problem of determining whether there is proxy use in this linear model would sort of boil down to looking for checking the intersection of this parallelogram with the region outside of the white circle and within the pink shaded regions, right? So basically, we can get a linear combination of alpha 1 and alpha 2 of sufficiently large influence and with association that's close enough to our original z that there would be proxy use. So the space of decompositions here are, you know, we can formalize them as vectors between, real vectors between 0 and 1, beta 1 through beta n, right? The notion of influence that we would get from this looks a lot like the influence we had on the previous slide, except instead of looking for equality, because it's a regression model, we're taking the squared error between the original model and the intervened on decomposition of it, right? One final nice thing about this framing is that checking for proxies can be formulated as a constrained optimization problem. It sort of resembles a second order cone problem, which, when the objective is convex, these can be efficiently solved. The objective that we get here is actually not going to be convex. So the way that we do sort of efficient checking for proxies in this setting is by a sort of conservative relaxation of it as a linear program, and that lets us sort of do the usual conservative check where we might get some false positives, but we're never going to get false negatives. All right, I am, what is it, 2:52 or 1:52 your time. So I'm running a little short on time. I might end the discussion of proxies here, and I could either take questions, or I could try and sort of quickly recap some of the work on membership privacy that uses these notions of influence.
There are no questions. You can continue, because there's already been a bunch of questions.
Yeah. Yep.
We slowed you down.
No. It's I also find
it's
that
Somesh Manley.
It's always Somesh's fault. No, I find I don't go through slides as quickly when I'm giving remote talks like this. There's just something about being comfortable at home. Okay. So the next sort of problem that we'll look at is related to privacy and machine learning, and it's known as membership inference. So here we're sort of talking about an adversarial scenario where an attacker wants to determine whether a given point that they have access to was in the training data for a model. And a couple of years ago, one of my PhD students, along with Samesh and Irene, wrote a paper where we sort of formalized this notion of membership inference as a sort of like formal game, which gave us nice definitions. I won't go into detail here, but basically, some of the things we're able to do with these definitions is like formally link membership inference to differential privacy, and come up with like concrete bounds that give conditions on like how membership inference resistant am I at a particular level of differential privacy, for example. So like I'm really interested in why something like membership inference would be possible in the first place in a machine learning application, right? Because it really does seem to contradict like the whole point of doing machine learning, where we want to learn something useful that generalizes to new data that we haven't seen from lots of examples that we have available to us, right? And so if all that we're doing is really just kind of in some sense memorizing some of the data that we've seen, well, first of all, there's a question of how well can we really expect to generalize to completely new data, but also, of course, it seems like maybe we don't have to do that, even if it works well performance-wise to memorize some data. If our ultimate goal is to generalize, then maybe we can do machine learning in a truly private way without having to memorize. So sort of one key idea is that overfitting, sort of framed as poor generalization in the loss of the learning objective, is sufficient for membership vulnerability to happen, right? But one sort of surprising outcome from this work with Sam and Somesh and Irene was that overfitting is not necessary for membership vulnerability. And so there we sort of leveraged the fact that our definitions looked a lot like crypto definitions and reused some proof techniques, from cryptography, and basically showed that there exists some, like if I have a stable learning rule that is not going to overfit, then there exists like always some closely related learning rule, which is also almost as stable, right? But it admits a membership attack that has near perfect advantage for the attacker, right? So I can have a stable learning rule, right? But then, like anytime that is true, there exists a related rule that essentially memorizes all this training data and makes it available to an attacker very efficiently, right? So that was kind of like interesting and curious, but it wasn't clear that like this is something that's really going to happen in practice, because the way the proof went was, the model that it sort of constructed to prove this existence was pretty unnatural. So since then, we've been thinking about like whether this could really happen in practice, right? Like whether a model that appears to generalize very well could in fact be memorizing a lot of information, specific information about its training data. Our sort of hypothesis was that the way the trained models make use of the features that they learn could potentially provide evidence of membership. And so a sort of cartoonish example here might be, say that we have a data set that, our task is to predict celebrity A or celebrity B from some picture. Sort of in real life, both celebrities are equally likely to wear sunglasses, right? But for whatever reason, just by chance, the training set that we have has celebrity A and sunglasses half the time, and celebrity B much less frequently, right? If this happens, then it's certainly reasonable and consistent with the learning objective to learn a feature that recognizes sunglasses and encode an association of that feature with celebrity A, right? So that when we're done training our model, if we're given an instance of somebody wearing sunglasses, right, there's actually going to be a feature, sort of some portion, some computation in the model that identifies sunglasses, right? And that feature is going to be influential on the prediction of an individual as celebrity A, right? So the question is like, does this actually happen? If so, how do we identify it? And how well does it let us learn information about the training data? Well, the first question has an affirmative answer. It does happen. So these pictures are from a popular benchmark data set called Labeled Faces in the Wild, where, what we trained the model to do here was predict the identity of the person pictured in the data. Right, and we also, because we're trying to understand, how the model made its classifications, computed sort of explanations or attribution maps of the model's prediction for the right class. Right, so below we see instances from the test set of Tony Blair and a visual depiction of the features that were most influential in predicting Tony Blair. On the right, we see an image of Tony Blair from the training set with this distinctive pink background, and the most influential features that the model used in that case look quite a bit different from those in the test data, right? So that's kind of interesting. If a little anecdotal, it still seems like weak evidence to use in support of an inference that this Tony Blair was a member of, this picture of Tony Blair was in the training set. But it turns out that we can, in fact, use information like this to make our inferences. And the way that we do that is by treating this feature use characteristic like an inference problem. Right, and in the simplest case, sort of think of the distribution of like feature importance as following like two normal distributions. We'll say that n star is the ground truth, true training distribution, and hat is the training sample. Right, if we want to predict whether a given sample is more likely to have been drawn from the true distribution or the training sample, right, we can build a model to decide for us. Right. In this case, basically what that model is going to do is draw a threshold where these two distributions meet, right? Anytime that our z is to the right of that threshold, we're from n hat. Anytime we're to the left of that threshold, we're from n star, right? So that's sort of the basic approach that we want to take to doing this. But the challenge is that we don't know what the correct feature distribution of the target data distribution is. Right? Because we're talking about internal features to a model, right? Not explicit sort of features given in the data. To make matters worse, the set of internal features that a model learns are going to vary between training runs, right? Even if we train the same model twice, but with just a different sort of initial state, chances are that the model is going to learn slightly different features, kind of in a slightly different order. So it makes it difficult to actually measure this true distribution to build such a predictive attack model. So the way that we do this is to leverage the same sort of influence metrics that we used for proxy use. Right? In a sense, we're sort of treating this as a kind of proxy use problem, but for kind of a different notion of proxy. Right, and so what we do is to estimate the true distribution of feature importance, freeze the network up to a given layer. Right, train proxy models, basically train the weights above that layer on identically distributed data to the training data, right, and then measure the importance, the influence of those internal features on their prediction outcome, right? So once we have this, we know what normal feature use looks like, right? And so we can build an attack model to characterize sort of abnormal, anomalous feature usage that might be indicative of membership in the training data. And I won't go into the results too much, but basically, like, one of the neat things about this is that indeed, even on models that have ideal generalizations, so we're talking about like a Bayes optimal predictive model that really doesn't overfit its training data at all. This attack does about as well as the sort of provably optimal strategy for the corresponding distribution, and almost as well as a sort of idealized attacker that has even more information than the threat model assumes. Okay. All right, so I know I've taken you past 2 o'clock. I apologize for that. I'll wrap up with a summary slide really quickly, and then take whatever questions you guys have. So thanks for coming and listening. I guess the sort of takeaway points are, by now you probably all know that machine learning systems are being used in some very important settings. And the fact that we can't really get inside them and understand them in the same way that we can understand programs that humans write, right, introduces some pretty unique risks. So sort of the overarching goal of a lot of this work and the work that I do is trying to sort of develop ways of better understanding how these models work, right? Whether they're making good decisions for the right reasons or accurate decisions, but for questionable reasons, or whether they're leaking training data unwittingly, so that we can sort of use that knowledge to like address specific models in various case studies, or develop like better techniques that don't have these issues to begin with. All right.
Thank you.
Thanks.
Yeah, I didn't know about this work on privacy using influence. That's cool. I should read that paper.
Yeah, it's quite recent. I think Klaus presented it in August at Usenix Security.
Cool. Yeah. Thanks again. Are there any other questions before Matt disappears to take care of babies? All right. I guess.
Wait, this is Tom.
Yeah.
Matt, it seems like you might have an angle on explaining things like dropout or hide and seek.
And like in terms of
of their effectiveness in generalization. I don't know. Maybe I'm
yeah. So dropout is definitely something that we've been interested in. Like, okay, for those that aren't machine learning people, which I wouldn't expect people at the Peel seminar to necessarily be, dropout is a technique that you can use when training something like a neural network, where basically during training, each time you go to update the weights of the model, you sort of randomly zero out some of the weights, right? Like you're going to sort of pretend like those neurons don't exist, and just rely on the others. And sort of one idea is that dropout is going to sort of act like a regularizer. It's going to sort of force the model to to potentially learn maybe like simpler concepts, or encode redundant information perhaps, and in general, I guess, kind of avoid overfitting to the training data that you have, because like half the time the previous update that you made isn't going to be relevant for the next. So one of the things that we did do with the privacy experiments was look at the effect of dropout on membership inference, and it did have some effect, but it wasn't as great as you might have expected. So dropout was sort of effective at getting the accuracy of our membership attacks like sort of back down to where it might have been comparable with a black box attack, where we didn't look at any of the internal sort of details of the network, which is somewhat interesting. But it was still like better than a coin flip in predicting whether a given point was memorized or not. Another sort of interesting thing about dropout is this question of like, does it really promote like learning some kind of a distributed representation in the layers where it's active? And that's something that we've been interested in using these sorts of like influence tools to follow up on, and see if there's a notable like characteristic difference between like the influence profiles of models trained with dropout and without. But I don't have anything concrete on that yet.
Cool. Thanks, Matt.
Actually, wait, I was fumbling with my phone. I guess what I was thinking is that there might be, it sort of might make your ideas about finding proxies harder, because dropout would cause things to be more smeared out, kind of like a hologram or something.
Yes, absolutely. So that's one of the slides I sort of skipped over. So we have kind of started looking at detecting proxies in deep networks. We have a nice influence measure for it that satisfies like similar sorts of axioms to the other influence measures in simpler settings. But the problem is like these things are just so big, you know, that whereas with linear models we could frame the search for proxies sort of as this nice convex optimization problem. Like there's no hope of doing anything like that with a deep network, it's not something that can be brute forced at all. So like there's this question of how do you go about finding proxies. One of the things that we like the best approach, the best luck that we've had are falling back on heuristic testing. Like instead of treating it like a program analysis problem where we're actually looking at the model, we try and find sets of inputs that might like create behaviors that are indicative of proxies being in the model, right? And then once we have some of these concrete instances, then maybe we can look closer at the parts of the model that are influential on those points. So like the way that we do it is by framing it as optimal transport, or framing basically using optimal transport theory to construct a mapping that lets us sort of create pairs of instances that differ along the protected attribute. So say that the protected attribute was gender. We then want to create a mapping that like maps the distribution of males to the distribution of females in a way that minimizes some notion of cost. And we can do that. There's a nice sort of theory for that, various ways to actually build this mapping. And once we've generated these pairs of instances, on querying the model, if we're seeing lots of changes in outcome, then it suggests that maybe the sort of variable that we use to break the data apart in the optimal transport mapping has a proxy inside the model. And we can use like these influence techniques to look for parts of the model that are influential and construct explanations for those parts. So like this is an example from an ImageNet model that's pre-trained, comes with TensorFlow. It classified this picture of Usain Bolt as a basketball pretty confidently, I might say, for being like 1,000 classes. If you look at, so I think we looked at like one of the sort of lower down convolutional layers of that VGG model, identified the set of neurons that were most influential at that layer in the prediction of Usain Bolt as a basketball, and then visualize those, sort of find the receptive field in the image that influence those internal neurons, right? That suggests something about like what the model has learned that's influential on its predictions of basketball. Like, and here it's highlighting Usain Bolt's face, maybe a little bit of his leg, right? So it's not like it saw something that it thought looked like a basketball in the background. It seems like there might be a proxy for like apparent race in predicting basketball, right? Sort of further supported by this 25% picture, where it didn't just get Usain Bolt, it got the leg of the guy who's running next to Usain Bolt and the head of the other guy next to Usain Bolt, right? So using these test inputs, we can start to like drill down on parts of the model and identify things like proxy use. But I don't think we've done that for anything like dropout. And you make an interesting point that like if there really is a distributed representation, that I think that does make the problem more complex.
Okay, thanks. Thanks for the great talk.
Thanks.
Yeah, thanks, Matt.
Yep. Thanks everyone.
Hope to see you in Madison soon.
Yes, hopefully, and maybe even in Pittsburgh soon too.
Yeah.
Once the world opens up again, we can all see each other where we are.